All right, when you are asked to graph in my math lab, I just wanted to go over what it looks like and the parts that might be requiring explanation. So it starts with just this pointer. You want to move it over. If it's a linear equation, you want to move it over to the line. When you're on the line, you can only use 2 points. If you try to do a third point, it'll think it's a new graph. Okay, so don't worry about a third point. You can only do 2. If you need to clear it, you can hit clear. That clears everything. If you have multiple lines, which I don't think you will, you can delete one at a time. If you are not graphing a linear equation, you want to use either the parabola tool or the absolute value tool. So that helps. Gives you some information on what an absolute value graph looks like. Here's a sideways parabola, and then we'll do circles later. So just make sure you've selected the thing you actually want to do. And then you also have the option of whether you want to use that as a solid line or as a dashed line. The dashed line would only come in for greater than or less than values. Good. If the question asks for your 2 intercepts, for an intercept, you need to use the intercepts that you found as your points. So if this is your line, and you instead of choosing your y-intercept and your x-intercept, you did the same line, but you started it here and only used this, they're going to mark it wrong, even though it's the same line, because you didn't select both intercepts. If your only intercept is at 0, 0, that's okay. And then just pick some other line, some other part of your line. But if they're asking for intercepts, they're going to want both of them. And never try to plot 3 points, and make sure you know how to clear it. And if something comes up, you can screenshot what came up and send it to me. And I can, if like your answer is very close, but it just didn't work correctly for you, I can mark it correct. Or if you have a question, obviously feel free to ask that question. I will get back to you. All right, graphing equations, intercepts, and symmetry. Again, I strongly encourage you to use Desmos for all graphing, but it is good to know how to graph, so you can do things by hand as well. So for when we are graphing an equation, what we're doing is we're saying that every point, which is just this, right? 2 numbers, an x value and a y value. Every point on the graph of that equation satisfies the equation mathematically. So here is the equation 3x minus y equals 9, okay? The point 3, 2, is that x, y value, is that coordinate point on the graph of this line? If it is on the graph of this line, if we were to just put it into a graphing calculator, then that means that when I put in 3 for my x, my y will be equal to 2. Right? That's what that point means. That point means that when x is 3, y is 2. This one means when x is 2, y is -3. Good. So if you want to determine whether the points are on the graph, you can graph the equation and then put in those points, or you can do it mathematically and say 3x minus y equals 9 when x is 3 and when y is 2, will this still be true? Okay, that's what they're asking you to do. So we can solve it. 3 times 3 is 9, minus 2 is equal to 9. So that's not true. So we would say these points do not satisfy the equation. Sorry, these points do not satisfy the equation. They are not on the graph. Good. There are the single point. There's only one point. But this would be the point 3, 2. right? 3, very bad at it. It should be over here. Make it very wide point. Over here. 3 on your x-axis, 2 on your y-axis. It is not a part of this line. Now the point 2 on your x-axis, -3 on your y-axis would be over here. And they want to know, is that part of this line? All right, so same thing. We're just inputting 2 for x and -3 for y, but same equation. 3 times x minus y equals 9. 3 times 2 is 6, minus a -3 is going to be +3 equals 9. So that is true. So this does satisfy the graph of the equation. All right, so we're going to be making a lot of tables today. X, 3x minus y equals 9. And what are my x and y? So we decided that when x is 2, 3 times 2 minus y equals 9 gave us the value of 2, -3, right? So if you were to solve this, 3 times 2 is 6, 6 minus y equals 9, subtract 6, -y equals 3, so y equals a -3, right? Sorry. Good. And then maybe one more point. When x is 0, what is y? Good. So now I have 3 times 0 minus y equals 9. 0 minus 9, sorry, minus y equals 9. -y equals 9. So y is going to equal -9. So this is the point. 0, -9. So now I have two points, and I can graph that line. Again, they're always going to be solid lines until we get to greater than or less than graphing inequalities. Good. So that's my graph. Feel free to check it in Desmos. So that was 3x minus y equals 9. Don't be afraid to put it in no matter what format they give you the equation. You should be able to put it into Desmos, okay? And they asked for the point 3, 2 was the first one. That is not on the line, right? And then they asked us about the point 2, -3. That is on the line, right? And then we found the point 0, -9. Let's see if I was doing math correctly. That is also on the line. Good. So that's what they mean by it satisfies the equation. It makes the equation, it makes this side of the equation equal to this side of the equation, and therefore it is on the graph of the equation. Every point on that line is true for that equation. Okay, so for this 3x minus y equals 9, when x is 0, or sorry, when y is 0, x is going to be equal to 3. When x is 5, y is going to be equal to 6. If you plug those numbers in for x and y, you will get a true statement. That's what it means when we are graphing an equation. All right, so for example 2, they have asked us to graph the equation y equals -3x plus 3. This is a linear equation. Linear means it is a straight line, okay? Anytime you have x raised to a second power, maybe y raised to a second power, you won't have a linear equation. Absolute value of x is not a linear equation. Radicals are not linear equations. But if x is just, it maintains it doesn't get raised to any power and it's not under anything, it can be linear. Good. All right, so to graph this equation by hand, what you're going to do is you're just going to find really low values for x, plug them into your equation and find the y. All right. So for example, it's going to be cramped. X is -2. That means y equals -3x plus 3 becomes y equals -3 times -2 plus 3. And when I solve that, I'll get a y, and that's the second half of my point. The first half of my point is going to be -2 something. And then my y value I find by plugging in -2, outputting the y. That's why we call the x the input, the y the output. The x is the domain, the y is the range. Good. So y equals -3 times -2 plus 3. -3 times -2 is a +6, right? 6 plus 3 is 9. So my first point is -2, +9. Now I have when x is equal to -1. So now I have y equals -3 times -1 plus 3. -3 times -1 is just 3 plus 3 is 6. So that point's going to be -1, +6. When x is 0, y equals -3 times 0 plus 3. Y equals -3 times 0 is just 0, right? 0 plus 3 is 3. So that's the point 0, 3. The only reason I wrote them over here is because I thought I would be using this space, but not as cramped as I thought. All right, when x is +1, y equals -3 times 1 plus 3. So that's just -3 plus 3 is 0, right? So when x is 1, y is 0. Y equals -3 times +2 plus 3. So that's -6 plus 3, which is -3. So that becomes 2, -3. So here are a bunch of points that I can now use to create a graph. My x goes from -2 to +2. My y goes from 9 to -3. Good. All right. So try to find like the smallest numbers in both columns. So 1, 0. 1 on the x, 0 on the y is right here. That's one of my points. Okay. 0, 3 means 0 on the x, 3 on the y is another one of my points. It's always nice to graph your value when x is on the x-axis, when y is 0, and on your y-axis when x is 0, just in case my math lab wants that and you fail to notice. For x equals 2, y becomes -3. And it looks like those are all staying in a line, so that's probably enough points for me. I feel confident about my graph. So that is how you would graph the equation y equals -3x plus 3. You can also go into Desmos. We'll put in y equals -3x plus 3. Up here is a gear. It says edit list, but oftentimes after you put in an equation, it will offer you to convert that equation to a table. So then it will tell you for each x value what the equation is equal to or what y is, okay? So when x is -2 over here, y is a +9. When x is -1, y is 6. When x is 0, y is 3. You can also put in your own value. When x is 100, y is going to be -297, okay? It won't let you edit the y values, but it will let you type in the x because x is your input, y is your output. So if they're asking what is x equal, when x is 50, what is y? You can create a table, put it into Desmos, create a table, and then input the x value that you're looking for. Good. And it doesn't have to be whole numbers. So that's example 2. We're just graphing a linear equation because it is a straight line. Now we have the equation y equals 1/2 x squared. You're welcome to just put this into Desmos. Because of this is not linear. X raised to the second power means my line is no longer going to be straight. Okay, but we're still just taking, the reason I chose x is 0, -1, -2, 1, and 2 is because these are the smallest numbers to do the math with, right? It's hard. It's hard math, so I want the easiest numbers possible. So if I were to, I would say start down here at 0, but then I'll mess up all my spacing. So I'll start at -2. Y equals 1/2 times -2 squared. Good. -2 squared, it has to be in parentheses, right? Because we're inputting a number for this. This is being raised to the second power. So -2 to the second power is a +4. 4 times 1/2 is the same as dividing 4 by 2, right? 4 times 1 divided by 2 is just 2. So when x is -2, y is a +2. Any questions? All right, when x is 1, or sorry, -1, that means -1 squared is just 1. So we have 1/2 times 1, so that's just 1/2. So when x is -1, y is 1/2. When x is 0, zero squared is 0 times 1/2 is 0. So that's just the number, sorry, the point 0, 0, right? Because 1/2, 0 squared is 0. 0 multiplied by anything gives us 0. When x was 0, y then becomes 0. Now I'm going back to 1 squared times 1/2. Back here it was -1 squared by 1/2, and we got 1/2 times 1, which is 1/2. And I'm going to get the same answer here because 1 squared is the same as -1 squared. So 1 squared is still 1. 1/2 times 1 is 1/2. So when my x value is -1, my y value is 1/2. And when my x value is +1, my y value is 1/2. Last one is 2. So y equals 1/2 times 2 squared, which is 1/2 times 4. So that means when x is equal to 2, 4 divided by 2 is 2. Okay. So now I have we'll call this 1. Good. Here's my graph. -2, 2. X is -2, y is +2. -1, 1/2. 0, 0 is the origin. And then 1 goes back to 1/2. So this x squared graph is mirroring itself from the, we call this the vertex, and it mirrors itself as we move away from the vertex. So 2, 2, -2, 2, or the line of symmetry. Good. Very not good at drawing curves. You just graph it like that. And you're welcome to check in Desmos to make sure that all of those points are real points on that real graph. Good. All right, we need to also talk about intercepts. Intercepts, to intercept just means to cross something, right? So The intercepts of a graph are the points, if there are any, okay, so sometimes there are not any, the points, if any, at which a graph crosses or touches the x-axis or the y-axis. So right here where we see x, that is our x-axis. Y, this is our y-axis. So on the y-axis, if you think about the y-axis, every point on this y-axis, x is equal to 0 on this y-axis. This is the point 0, 2. This is the point maybe 0, 5.5, but we'll call it 6. Good. This is the point 0, -4. Everywhere on this line, on this y-axis, x is equal to 0. On the x-axis, y is equal to 0. Here's the point 4, 0. Here's the point they already labeled it. I'll label it again. -4, 0. Here's the point 0, 0 because it's on both the x-axis and the y-axis. Good. So the y-axis, for the y-axis, x is always 0. For my x-axis, y is always 0. To find your y-intercept, that means I want to know when does my graph cross the y-axis. Y-intercept is asking when does the graph cross the y-axis? So you just say when x is 0. You can find your y-intercept when your x is 0. You can find your x-intercept when or where y is 0. My x-axis has a y value of 0. My y-axis has an x value of 0. So to find the intercepts, you find the places for the y-intercept, x equals 0. For the x-intercept, where y equals 0. Okay. If you're just looking at a picture, you can just remember that this is x, right? So my x-intercepts are where it crosses x. -4, 0, and this one has 2, 3, 0. Those are my x-intercepts. +3, 0. And you see the format is x, 0 because y will always be 0. For my y-intercepts, set x equal to 0 and solve for y. So that's only the point 0, -3. Good. So for the y-intercept, again, it's going to be 0, and then whatever your y value is. Your x-intercept is going to be x value, and then, oops, I'm sorry, you couldn't see that. X-intercept is on the x-axis, y is equal to 0, so you can write it as a number, and then your second number is going to be 0 because that's your y value. For the y-intercept, x is 0, so it's going to be 0, whatever your y value is. Good. Find the intercepts of the graph of y equals x squared minus 9 and then graph it. So if we needed to find the values of the intercepts without graphing it, you would just take your equation for the x-intercept, remember, y is 0. For your y-intercept, x is 0. So that same equation, here we're going to set y equal to 0. Here we're going to set x equal to 0. When y is 0, what is x? That will be your x-intercept. So the equation was y equals x squared minus 9. Now that's 0. 0. equals x squared minus 9. Now I'm just going to solve for x, so I'll add 9 to both sides. That's now 9 equals x squared. Good. To get rid of a squared, we take the square root of it. Remember, though, when you take the square root of something, you have to include the positive answer and the negative answer, because the square root of 9 is 3. Your calculator is only going to give you your most popular answer, the positive one. But that's because 3 squared is 9, but negative 3 squared is also 9. So when you take the square root, you have to take the positive answer and the negative answer. Okay, so that becomes, we said it's 9, so it's negative 3 and positive 3. That square root cancels the square. So there are 2 x-intercepts. So x is 3 when y is 0, and x is negative 3 when y is 0. When y is 0, x is negative 3 and 3. Good, and those are my x-intercepts. When you think about where those points are, it'll become clear whether they're your x-intercept or your y-intercept. Good. Now for your y-intercept, x is 0, so that same equation, y equals x squared minus 9, a little bit easier. Y equals 0 squared minus 9, right? So y equals 0 squared is 0, 0 minus 9 is a negative 9. When x is 0, y is equal to negative 9. Oops, sorry, when x equals 0. So that point is 0, negative 9. You see how for my x-intercept, I put the x value first and then the 0. For my y-intercept, I put the 0 first and then my y value. And then we can graph it, see if that is true or not. I mean, I guess the only way to see if it's true or not is to use an application, but we'll graph it. All right, so it was my x-intercepts are negative 3, 0 and 3, 0. Here's negative 3, 0. Here's positive 3, 0. And my y-intercept was 0, negative 9. So from my origin, if I go on the x-axis, I don't move on the, or sorry, I'm on the y-axis, but I don't move left or right on the x-axis because it's 0. And then for my y-axis, I go down 9. So that's 0, negative 9. And then to find these on my x-axis, I go negative 3, so 3 to the left, but I don't go up or down for y. And then over here, I go 3 to the right and not up or down for y. Now let me draw a terrible curved line. There's my graph. And then you can check it in Desmos. That was y equals x squared minus 9. So x squared is just right through the origin, and then we subtract 9, so we move it down 9 places. All right, the last thing we are going to practice is testing for symmetry. Symmetry means that you can mirror something. If it's exactly the same, how would we say it? Symmetry. Both sides kind of like exactly mirror one another, okay? So we're going to talk about symmetry with respect to the x-axis, symmetry with respect to the y-axis, so this is your y-axis, Here's our x-axis. Good. Third way is symmetry with respect to the origin, which just means is it symmetrical according to the origin, just that one point, no line, and then how to test for that algebraically. Then we'll be done. A lot though. All right, symmetry with respect to the x-axis. A graph is symmetric with respect to the x-axis. IFF means if and only if. For every xy on the graph, the point x negative y is also on the graph. Good. If the graph were folded along the x-axis, it would lie on top of itself, or if I put up a mirror right here, each side of the mirror would reflect the other side, right? This looks like a mirror of that, which obviously means that looks like a mirror of this. All right, so what does it mean? Every point xy, the graph has the point x negative y. What does that mean? I'm going to make up what each of these is, right? xy, x negative y. So if this is 1, 2, this is going to become 1, negative 2, right? If this is the point 3, 2, then this becomes the point 3, negative 2. Yeah. Then this is probably 4, still 2, 4, 2. Here's 4, negative 2. So each y just became its negative. And same for this one, right? Negative 2 became 2. It became its opposite. It took on the opposite value. Good. So this line mirrors this line. Down at the bottom, it says, if a graph is symmetric with respect to the x-axis and the point, because obviously this is the x-axis, and the point 5, 3 is on the graph, what other point must also be on the graph, right? And our rule is when or if xy is on the graph, it must also contain x negative y. That's what it says up here, right? For every point xy, we also have x negative y. Ooh, computer's about to die. 1 second. Good. So that's our rule. And in this case, xy was 5, 3. So x negative y will be 5, negative 3. What other point must also be on the graph? The point 5, 3. Oh, sorry. The point 5, negative 3. Comfortable? Y-axis, the rule is for every point xy, the point negative xy is also on the graph. So now the axis that we're putting the mirror to is the y-axis. This side mirrors this side mirrors this side. Good. All right, so whatever happens right here is also happening right there. Exactly the same, okay? So this guy was same x value, 1, 1, 3, 3, 4, 4. Opposite y value. Opposite y values. Again, don't write down everything I say if it's not helpful. Good. Everything is equal distance from the x-axis. So what we're measuring is this amount right here. This distance is the same as this distance, right? This distance is the same as this distance. Equal distance from the x-axis. Here, if you think about distance, we're taking the distance from of each point from brackets are hard, from the y-axis. So equal distance on both sides from the y-axis. The first example, we were equal distance from the x-axis because we were symmetric on the x-axis. Now we're equal distance from the y-axis. And therefore, we have the same y values for all of them. And opposite x values. If the graph were now folded along the y-axis, it would lie on top of itself. Good. So if we were to make up some points for these guys, maybe this is 1, 2, -6, 2, right? Same y values, opposite x values. So instead of -6, 2, equal distance from the y-axis on the other direction would be a +6, 2, right? If this is 3, 4. If this is 4, 1, -4, 1, I apologize. Then this has to be 4, 1 for this to be symmetric. Good. All right. If a graph is symmetric with respect to the y-axis, the point 5, 3 is on the graph. What other point must also be on the graph? So the rule is every point xy when it contains xy, it must also contain -xy. Again, xy is the same. Xy is still 5, 3. Now we're going to make the x the opposite of 5. The opposite of 5 is -5. Keep the y the same. So this can just be as simple as, what do you need to switch, right? If it's respect to the x-axis, switch your y. If it's respect to the y-axis, switch your x. The origin is not a line, it's just a single point, okay? A graph is symmetric with respect to the origin if and only if for every xy, the point -x, -y is also on the graph. So now we're changing both the x and the y values. Instead of holding a mirror up anyway, you are turning the entire graph upside down. Okay, so think about, and if this is an exam and you are trying to figure out if it's symmetric with respect to the origin, here for these guys, you can hold up your pencil, right, to the x-axis. You can hold up your pencil to the y-axis. For the origin, what I like to do is I describe the graph. This is moving towards -infinity on the left, right? It curves down on the left, goes through the origin, it curves up on the right, and then comes back to the x-axis, and then it goes towards +infinity to the right. Then I turn my graph upside down, and I decide if I can describe it the exact same way, even though the graph is upside down. Good. Or you can just take it has to be a different piece of paper so that it doesn't get turned upside down, but you can draw your graph on that other piece of paper. So you can go, you can turn it upside down and say, yeah, same graph. Good. So it's symmetric with respect to the origin, means you can turn it upside down and it looks the same as it did right side up. Good. All right. Instead of being equal distance from the x-axis or equal distance from the y-axis, it's equal distance from the origin. Each point is equal distance from the origin. Good. Nothing stays the same. So my X values are opposite. And my Y values are opposite. Good. So that means anytime I have negative X, negative Y, I must also have positive X, positive Y. I almost made it negative. Negative 2, negative 1 becomes 2, 1, right? Negative 1, negative 2, confusingly, becomes positive 1, positive 2. Good. All right. So if a graph is symmetric with respect to the origin and the point 5,3 is on the graph, what point must also be on the graph? When we have X, Y, we must also have negative X, negative Y. Good. So X, Y was 5,3. It also has to have negative 5, negative 3. And then just final example is, or sorry, final new information is testing for symmetry algebraically. So we know what it looks like in a picture, but if we need to test an equation for symmetry without graphing it, to test for the x-axis, replace y with negative y and then simplify. X-axis, y becomes negative y. And then is it the same equation? Okay. Just like if we looked at respect to the x-axis, all y's become negative y's. All right. So if you make your y a negative y, do you end up with the same equation? For 9x squared plus 16y squared equals 25. Instead of y, I'm putting in a negative y. Replace y with negative y, simplify it. 9x squared plus 16, negative y squared is the same as y squared. So that is simplified. If I simplify it and I get the same equation back, it is symmetric. So that's for the x-axis. For the y-axis, x becomes negative x. Okay. So now instead of 9, x squared plus 16y squared equals 25, I have 9 negative x squared plus 16y squared equals 25. And again, they're just asking you to simplify. Negative x squared is the same as x squared, right? 2 negatives will make the same positive as 2 positives. Right? All we changed was one sign, but since we're squaring that number, it does not matter. So that is symmetric on the x-axis. It is symmetric on the y-axis. And then for the origin, what does it have us do? Replace x and y with negative x and negative y. So we're making both of them negative. So we have 9 times negative x squared plus 16 times negative y squared equals 25. Because I'm squaring that, it is the same as a positive. So this is symmetric with respect to the x-axis, the y-axis, and the origin. Good. I will put it into Desmos. We can see that that is true, and then I will let you go. All right. So the graph was 9x squared plus 16y squared equals 25. So if I were to mirror that, if I was to put a mirror on the x-axis, it would be the same graph on both sides of that mirror. If I put a mirror on the y-axis, it does mirror itself on the y-axis. And if I turn it upside down, it will still look like the same circle upside down. So that does ring true that it's symmetric on the x-axis, symmetric on the y-axis, and symmetric on the origin. Now, I know we didn't finish everything, but all right. On the x-axis, so we know what our x-axis is every point above the x-axis mirrored below the x-axis? Yes, it is. Equal distance, right? Same on the y-axis. Anything from here at negative 1.6670 is mirrored at positive 1.6670, right? Our next example that we have not covered yet was this picture, okay? So oh, I'm sorry, and I didn't talk about the origin. It's also mirrored on the origin because this 1, 1 means I must also have negative 1, negative 1. Is that true? I do. It's hard to get there. Good. So our positive x, positive y has a mirrored negative x, negative y from the origin. The next graph was 6x squared over the quantity x squared plus 2. This is not going to be perfectly symmetric on the x-axis, the y-axis, and the origin, right? The test for the origin, if I'm looking at the graph, is I can turn it upside down and I have the same picture. So would we say that this graph is mirrored on the origin? If I flipped it upside down, would it be the same graph? No, right? The y-axis, so think about the y-axis, which is the vertical axis. If I held up a mirror on the y-axis, would I see, does the positive x side mirror the negative x side? It looks like it does, right? Negative 5.02, 5559, positive 5.02. I won't be able to get to it. Right? So those are mirrored on the y-axis. And then on the x-axis, so if you're looking at the horizon, the horizontal axis of this graph, is everything that is above the horizontal axis mirrored below that horizontal axis? It is not, right? Because there's nothing below the x-axis for this particular graph. So if I'm just looking at the graph, I'm thinking this particular function is only mirrored on the y-axis. So let's look at the math for that. Good. All right, so y equals 6x squared over x squared plus 2. What are our rules for symmetry? For the x-axis, which we said it is not, replace y with negative y and simplify. So instead of y, now I have negative y equals 6x squared over x squared plus 2. Is that exact? Does that simplify to the exact same equation? It does not, right? So that is not symmetric on the x-axis, which is also what our graph showed. For the y-axis, what do? We replace x with negative x. So instead of replacing y, we're just replacing x with negative x. So we have 6. Instead of x squared, it's going to be negative x squared over, negative x squared plus 2. If I simplify all of that, y equals 6, and negative x squared is the same quantity as a positive x squared, right? So this is, in fact, our same equation. So for the y-axis, it is symmetric. And for the origin, we have to replace x and y with negative x and negative y. Here I replaced negative y and I didn't get a true answer, so I don't think if I do it in this case, it will work any better, right? So whether you do it graphically or algebraically, you should get the same answer. So negative x squared is a positive x squared, so that one's okay. Here the negative x is the same as a positive x, but we still have a negative y, so that is not symmetric according to the origin, just like our graph told us, the picture of it told us. Finally, they ask us to graph the equation negative x squared plus 4 just by plotting points. Find intercepts and check for symmetry. Do you feel comfortable doing that? Remember, your intercepts are very important, okay? So, x-intercept. How do I find my x-intercept? I set y equal to 0 because when y is 0, we are on the x. We are on the x-axis when y is 0. Good. Take that equation, y equals negative x squared plus 4. Change your y to a 0. 0 equals negative x squared plus 4. Good. Now we're solving for x, so I'll subtract 4. Negative 4 equals negative x squared. Square root both of those to get rid of that square. Let's not do that. Let's make it positive first. Divide by negative 1, divide by negative 1. So it's a positive 4 is equal to a positive x squared. No need to make things more complicated. I'm going to take the square root so that I get rid of that square. Remember that when we take the square root, we have a positive and a negative. Good. So here, x is the positive square root of 4, which is 2, and the negative square root of 4, which is a negative 2. Any questions about how I got those? So what that tells me is when y equals 0, x is equal to 2, and x is equal to negative 2. So those are actually points, okay? The point x, y, and this point x, y are my two x-intercepts. For my y-intercept, I'm going to say x is 0. Same equation, y equals negative x squared plus 4. Y equals negative 0 squared plus 4. Y equals 0 plus 4. Y equals 4. Good. So that means when x is 0, y is 4. That becomes the point 0, 4. Good. That is enough information to plot, kind of, right? So we start at 0, 4. And we cross the x-axis at negative 2, 0, and at positive 2, 0. Good. Just looking at what I graphed, where is our symmetry? We have symmetry along the our choices are y-axis, x-axis, and origin. We can test it algebraically, but I think it's only going to be along the y-axis, right? If I turn it upside down, I will not have the same graph, and I do not have the same above the x-axis as I have mirrored below the x-axis. So I'm just going to say it's only symmetrical on the y-axis. Good. The y-axis means I change it to negative x. So y equals negative x squared plus 4 becomes y equals negative x squared plus 4, which is negative x squared is the same as positive x squared. Good. So that is true. It does simplify back to itself because the x was squared. All right, so that is the end of 2.2. So I'm going to stop recording and start a new one.